Friday. Um, let's see. So the first thing I have to do is actually a design problem, not anything else. I want to go look at how everything appears when I try to build. And I sort of left off just making a huge mess of a lot of the API. And so today the goal is to recover as much of it as possible to a working state and to get the thing here working or a thing similar to it. I want to think through exactly what I want to provide in terms of this dynamically updated data structure. Basically, the problem that I'm dealing with is I want to be able to support the idea that you have different parts of the custom layer and you don't want to have to write a whole program that is interconnected with itself in complicated ways. You don't want to be the architect who figures out how information flows through everything, because even whether or not you're using other people's modules that you're bringing in, or you just want to be able to code up a module that's like 200 or 300 lines of custom code that doesn't want to think about all the other custom code you've ever written or all the custom code that comes by default with 4coder, right? There's just lots of things that want to be able to interoperate, and you want that to happen very seamlessly. And the biggest thing that's been preventing me from making that super seamless is the idea that there's this information you want to attach to different lifetimes, and we've started building up the API that manages a lot of that, or I've started building it up, and some of it happened on stream last week. But I'm not totally convinced that the thing I coded up last week is the best thing. It's the best thing for this, possibly. It's the easiest thing, it's the simplest thing to solve this problem, at least, of the marker list. But there's another problem that's very obviously connected to this self-modifying data structure, or sort of managed data structure, I should say, that, you know, there are other uses I might want that might not exactly match this, and there are optimizations that I probably would want here that aren't available right now. So I want to think about a couple of different use cases that look different and how I can reduce their differences. You look where to draw the layers, right? I'd like to avoid having too many different data structures internal to the core. In fact, I'd like to have just one, at least in this build, and I want the one that I put in to be able to handle the two use cases I have in mind. So I'm going to switch to actually Milton real quick to see if we can't think this through. Alright, so here are some of my thoughts. First of all, what we have is there's this divide. Right, over here we have the core, and then over here we have custom, right? And the idea is custom stuff wants to be sectioned off into modules like this that don't have to talk to each other, they only want to have to talk to the core. So anything where these guys need to cooperate should ideally, as much as possible, happen through the core brokering those cooperations, and not through you having to go and write the interoperations between all these layers yourself, right? Having to do these arrows would be a big problem, because that means if you've written these 3 layers and then some friend of yours sends you his code for his layer and it looks like this and has another layer here and they're sort of looking back and forth at each other like this, and then you look at it and go, well, really the concerns of this layer really relate to this, and now you have to do all this extra wiring to drop these new things in. If you ever cut them out, you then have to go and find that extra wiring and pull them out. So point is, as much as possible, we want to avoid the cooperation between layers happening in this sort of vertical way and only happening from the custom side to the core side, and the core side will do the routing of information in between all of these things that needs to happen for cooperation to work, right? It's going to handle all this what's a good word for it? Sort of intermixing, this cross-concern type thing, the communication problem. And if we write a good API that lets us express the kinds of concerns that each layer, each module might be likely to have, then the core can figure out how to translate those concerns coming this way into some sort of data structure, right, that it, understands or whatever, that that then can be translated back out to the other sides, right? We're trying to find small, well, not necessarily small, but good, easy to implement solutions that we can put into the core. Not even easy to implement. I guess what we want to find are ways of maximizing the chances that I can ship the core successfully without game-ending bugs, hopefully with as few bugs as possible, while giving as much bandwidth to these channels as possible, so that layers in the custom layer or modules in the custom layer can interoperate without having to draw those arrows right now, or in the future. Right now they're already drawing some of those arrows, and we kind of want to undo that. So what am I talking about in particular? That's an abstract idea of what I'm looking to build, but what in particular am I building in the core right now that's going to help with this problem? Well, right now there's this thing, the core has always had this idea of views and buffers, and views and buffers can be opened and closed by this arrow here, right? So a view can be opened from one of these modules, a view can be closed from one of these modules, a buffer can be opened or closed, and maybe this module here wants to keep tab of all the buffers that ever exist, and so it wants an arrow in for new buffer, and then this module here wants to create new buffers, right? New buffer. And the core basically has the job of linking these things up. Now this is already handled. Whenever one part of the custom layer creates a new buffer, this linkage happens via a hook. I kind of don't like the hook structure, but it might be the best type of thing. There might be a small variation on it sometime in the future, but that's the kind of notification that is useful for a new buffer. But then there's another type, which is close buffer. And suppose this thing here, which is tracking all the buffers, also needs to know whenever a buffer closes, and then let's say that this thing closes a buffer. And so what are we going to do? Are we going to connect these hooks here? Well, we kind of do that right now. We have a hooking system that lets us answer this question. But a lot of times what this custom layer here really wanted to do was keep a data structure and modify it whenever the buffer closed. So maybe this module here is sort of simulating like a stack of papers inside of a view, right? You have a view and it wants to say that every time you put a buffer on top, like into the view, you're putting a new stack of paper on top. Now that might be a stack of paper that you pulled out of the middle of that stack and put it on top, or it might be a stack that wasn't a paper that wasn't already in that stack and you put it on top. But either way, you have these stack of papers that are in the order that you've most recently viewed them, right? So the one you're viewing, the one you were viewing before that, the one you're viewing before that, and all the way down. And you want this so that you can have a nice predictable behavior of what happens when you go backwards through the stack and say pop things off and like pop, oh, there's the thing I was looking at a minute ago. Implementing something like that right now would be quite a chore, because you would have to build a data structure that is built by two callbacks, whenever a new buffer is created and whenever a buffer is closed, and then modify a data structure that's like a stack. And you would have to do that per view. Like for each view, you would be keeping a separate stack. And so it's just this really annoying problem. And if this layer is going to be doing that, this layer down here might be the one that handles jump lists, right? And so it also cares when buffers are opened and closed, because especially when a buffer is closed, because when a buffer is closed, it's going to look up into its table where that buffer is, and if that buffer has any jumps attached to it, and remove it from a jump list if it is in a jump list right now, right? It needs to go find the jump list in which that buffer participates and erase it so that it won't try to jump to it again. So then we end up in this really nasty situation where this event wants to communicate to both of these modules excuse me. And since that's being done through a hook, right, this layer here is closing a buffer, and that needs to get communicated to both of these modules, which both care when buffers get closed. By the way, hi Jim in the chat. So what happens right now is this is a hook, and if there are two different modules that both care about this, it's also, I guess I should say, it's not just a hook, but it's a single hook, like it's a single value hook. You can't chain hook handlers onto this hook. There's one handler for the hook, which means that these two now need to cooperate in order to share that hook, right? Now, one thing I could do, and you might be thinking, is just why don't you just change the hook system to let you register a chain of handlers onto a hook, and then we would be closer to what we want, because then they would at least both be able to get the message without ever drawing the interconnecting arrows, right? So that would actually solve this problem. I would be able to pass these events through the core and back out correctly, and I wouldn't have to do the interconnection between two layers that I'm trying, or two modules that I'm trying to avoid. But what I would still have to do is this module is going to be maintaining a data structure that it updates on these events, and this module will be maintaining a data structure, and they're going to have a lot of code in common. So now we have a problem, which is that are we going to have two modules both implement very similar data structures separately? Are they going to share a library that they both have a dependency on that implements that data structure for them? Or can the core provide that data structure? Can that core provide the data structure so that there is one way that these things can talk to each other, and not only will now neither of these have to write their own custom data structures, that not only will they be able to rely on a API that already implements a useful data structure, thus saving them time to write it, but also if two layers want to interoperate through something other than the text in the buffer, if they have, like, I'm building a list of jumps, and then another module is built on top of that that wants to be able to read that data structure, then there can be different ways of the two modules can perhaps think about each other's data in a way when they do want to cross over, because one of them is dependent upon another, in a sort of standard way that is the same for all 4coder modules, so that you can come to a 4coder module and look at it and go, okay, this is reaching into this data structure and reading what it does, and that's why it's dependent on this other module that set that data up, and I don't have to learn the specific dependencies of how the libraries get built for the data structures. Rather, it's just I can read the API. It's the same API that I'm used for everything else in the 4coder system, and so I already know how the data structure that they are using works, and I can reason about the modules. Young Lena, hello, welcome to the chat. When you say that's exactly what I was thinking, are you talking about the hooks thing, or what? And no, I'm not really optimizing. I'm optimizing in a sense, but what I'm really doing is architecting. I'm dealing with architecture type stuff. Now, I think hooks will be on something like a hook will always be there. Maybe not in a hook-like format. Hard to say. But one nice thing about having the core manage a data structure besides just these hooks is that allows me to I see. Yeah, well, the basic idea is already in the video, but yes, hopefully if you follow along a little bit it'll become clear again, because I don't want to repeat all of it. So the conclusion that I've come to is that I think I want to do this kind of thing, building a data structure inside the core, through which a lot of this can be avoided. The way this would look is, instead of having just direct hooks that tell other layers, other modules in the custom layer when an event has happened, so that they can interoperate like that, which leads to these nasty things of like, this makes a call, and that call comes into the core and enumerates a list of hooks, and then that calls into here, and then that calls into here, and hopefully none of these things make a call that come back in here and enumerate a list of hooks that leads us into a loop like this, because that's the kind of thing that can happen, and it's annoying. Even if that doesn't happen, it can still become like this really bad call graph that keeps on enumerating more hooks and calling into more layers and spiraling out of control. And what's annoying about that is, even though in that kind of architecture, when this event happens, it's somewhat predictable that all of the consequential events will occur right away. However many of them there are, they all just happen, right? Unfortunately, the thing that's bad about that is that's actually more surprising when the number of events hooked to this is larger than you anticipated. Like, sometimes you are trying to close a buffer, and then closing a buffer entails so much more change of state throughout the program than you expected, and all of the code paths light up in this really weird way that become impossible to unentangle from each other. So what I figure is, since most of those callbacks are just receiving new buffers and closed buffer events so that they can update a data structure, what if that data structure just lived in the core? And the basic data structures that I have in mind are, we will attach, first of all, there's a list of variables that you can get by index. So it's here's my sort of struct, you give me the input index / input name, and I give you a little 64-bit thing back. So now this custom this custom module can set a variable onto a view and then get it back later. And that doesn't interfere with the fact that this custom module here is also setting a different variable and getting it back. And when this view or buffer closes, all of this gets cleaned up automatically without either of these even needing to know about it. The memory is just gone. Those variables disappear. And if they query for them later, they'll get nothing back and find out that there's nothing there, and they can do something about it then. But that's not necessarily always going to be enough. So the next thing you can do is, in addition to having this sort of block of variables that exists once per object, an object being either a view or a buffer, there's also an arbitrary number of memory handles that you can put on there. So maybe this buffer has a memory handle from this guy, and a memory handle from this guy, and a memory handle from this guy. And then they have they're using variables to get back to those sort of larger buffers. So this variable here has a 64-bit value that is the handle back to this buffer, and now all of this will get cleaned up when the buffer closes. And so again, the way that this module here expects to reference its buffer, its memory object, is that it has a variable that it looks up. That variable gives it the handle, and then that handle gives it memory itself, right? If in that process it goes to look up this variable and the variable isn't there anymore because the viewer buffer has been cleared, then it'll immediately get back the message saying that the thing is gone and it can act correctly. Okay, so that's the next kind of thing I've already sort of set up to do, is having memory attached. The attached memory doesn't always have to be just plain memory. The attached memory can also be a jump list, or a marker list, right? So it could be that some of these attached memories have extra flags on them, like this is for markers, and maybe these are invisible markers. Invisible. And so now, whenever this buffer gets an edit command, maybe there's, one of these modules is just the basic commands, so an edit comes in that changes the buffer. Well, while that buffer is getting changed, this data gets modified, and then this module that put that set of markers there can later request that set of markers and get back the new positions of its markers that were changed by this module, right? That system's been in place for a while, and it was very successful at solving this problem of reducing the intermixing between layers or modules this way, right? And the reason it was so successful is because the core is told, here's something I care about, and then another module can do actions that have side effects on that thing that the first module cared about, and then when that first module comes back, it doesn't have to have received notifications that something happened to the thing it cared about. It just reads from the thing it cared about as if it hasn't changed and finds out what state it's in. Young Lena asks, are these structures you're coming up with yourself? Yeah, to some extent. Some of the, I mean, there's a lot of different ideas that I've learned over time, and I'm just composing lots of ideas. I haven't like researched how other text editors build their data structures for this purpose, although I have asked people what kind of things happen in Vim script and in eLisp and stuff. And from what I can tell, they just don't even, like, they either don't even handle this, or they handle it in weird ways, like by conventions, like, oh, we are going to do this intermixing of information via a buffer or something, and that text buffer will have in it the information you need to communicate these concerns. And so it's by convention instead of by API design, right? Instead of by design forced from the editor, which is kind of the direction I think I like. Especially because of the success of the marker system. I'm basically just taking the marker system and blowing it out to several more generic purposes. Now, that stuff I'm all happy with. I have no doubts about any of that. The thing I want to take some time to design before we get to the code is a slightly more sophisticated data structure that I was thinking about building last time. I'm still having some doubts about whether it's best. Young Lena, yeah, those other editors I talked about are open source, and I've read some Emacs source before. I wouldn't say it's particularly helpful because you have to talk to someone who actually knows those code bases to even find the thing you really care about a lot of the time. But you could go check them out if you wanted. Anyway, so the data structure I was considering building was to add the idea that there would be these sort of linked nodes that would be doubly linked nodes for doubly linked lists. Upon their creation, they would just link to themselves like this, and then there could be several nodes spanning several objects, right? And so what could happen is maybe you have one node sitting there, a different lifetime object here, so here's a buffer, there's a buffer, everywhere there's a buffer type of situation, right? And then start linking these things together. So this points into here, this points into here, this points into here, and then they all point back as well, right? Like boom, boom, and boom, right? So now these things are all doubly linked in both directions, and what will happen is the custom modules can create more of these blocks and put them into a list by saying insert this before or after this node. So you could just say make a new block and insert it right after this thing, right? And whichever one of these directions is the forward direction, it would get inserted like any doubly linked list. And then say this module has created this doubly linked list, and then say this module issues the call from the API that closes this buffer. Then this doubly linked list would automatically be able to be updated the same way that when we're freeing all this other stuff. These are just memory frees. This would be a little bit more complicated because it has to know all of the nodes it has and free them, and then update the linked list so that it doesn't have this or this and is just the two of these things pointing back and forth at each other, right? But then, once that has happened, right, well, I guess I could keep that actually for a moment here. Once that has happened, and these are both disconnected, and it's just these two in a list together, then when this module comes back to read its list has automatically been updated. So some things I like about this are, for the use case of the stack of all the most recently viewed buffers, this is exactly what you would want. You would say for a view, for a pair that's this view that I am making a stack for, and this buffer, create in that lifetime scope in that sort of managed scope, create a new node and insert it on the top of my list, right? And then you can have inside of each view a variable that points to the top, right? So if this right here is the lifetime for a view, then it points straight to the top like this, right? It could even point to the top by having a special top node that is inserted into the list that it points to, and then having that top node point in like that. And the reason I would do that is so that your top node can't get erased out from underneath you. And this is the kind of thing I'm still a little concerned about that I haven't fully thought through, which is basically, if I go with this, what does it mean to say I want to store a position in this list? If I store a pointer straight to this, and it's just living on some memory, for instance, if I store this guy's handle, so maybe this module here stores, well, we said it was this, yeah, so suppose this module here just stored this as the top of its stack. Boom, and it said, here's the top of my stack, I'm going to store that in this. And then this gets erased out from underneath it, then it will have lost any handle to the rest of its list, which isn't great. One option is to say, look, everything in this list should be, when you're building your data structure, build it in such a way that everything inside this list is a part of the view's scope as well, so that if the view closes, everything closes together, and then have one node that sits in the list that sort of works as a sentinel that's only a member of the view. That way, we don't have to store it here. We can say, go to this variable, have that variable, look up at that value of the variable, and that'll give me a handle to a sentinel, and that sentinel's next value is the first thing in the list, right? So using a sentinel type approach, we can track the list, and for that purpose I think this is perfect. There's be no other problems that I can imagine. You'd be able to look up all of these other nodes by saying whenever we store one, we have a little variable block that points to it that lives inside the same scope. And then when we have a view and a buffer together, we can find we can find the node for that view buffer crossover by looking at that variable for that crossover, taking that intersection, taking the variable as a handle to a node, and there's the node, and we can then pop it out of the list and insert it at the front of the sentinel, right? For the stack of buffers, this would work. For the jump list, it's not quite good enough. And the reason that this is not quite good enough is basically, let me back this whole thing up now. We're going to talk about the data structure in particular rather than the general problem that I'm thinking through. So the basic reason that this isn't quite good enough for the jump list is that the jump list is a lot like an array in the sense that it has some index ordering, and unlike the stack of buffers inside of a view, it doesn't ever really want to change that order, and in fact it doesn't want those indexes to ever get changed underneath it either. So say like these all belong to the first buffer that we have jumps for, and then we have like this is the second buffer, so buffer 1, buffer 2, and then buffer 3, right? So what can happen is when we first parse our jump list, we have all these jumps, and a jump consists of which buffer we want to go to. So like, let's say here's one of our buffers. Now that's the sign for a variable block. Here's one of our buffers. It's wider than a variable block, and it has a little squiggly line atop it. That's how you know it's a buffer. And it says, okay, I jump straight into this line in this buffer, I jump straight into this line in this buffer, and I jump straight into this line in this buffer. It's off the screen now, and so on, right? And so that's what a jump list looks like. And suppose that this buffer closes. Then what's supposed to happen? Question mark. Well, these jumps have just become invalidated, first of all, and then they were stored as markers on this buffer, right? So this buffer here has its little lifetime scope, and in there, among other things, it has a set of markers, 1, 2, 3, that match up with these 4 jumps. So each of those 4 jumps, the way it actually finds out where it is in the buffer is it goes, okay, here's my marker, and that marker takes me to here. And the reason for this is so that if text gets inserted right here, these markers get updated. Again, we're saying we want the core to automatically handle this concern. I care about these 4 locations in the buffer. Track them for me. And then if any other modules come in and edit this buffer after this is set up, these need to be staying correct. And then, as long as they're staying correct, when we actually activate the jump, we can look up the value that we need to, the new value, and without knowing whether or not it's been written to again, we can read it and jump to it. Much better than having to write a callback that updates the data structure. It just happens. But here's where things get weird. So this stuff is already kind of how the jump list used to work, but now we're hitting up against a part where it can fail, which is that when this closes, right now the way it has been working in previous versions, is that when this code set up this data structure and set up this marker array right here, it also registered a hook. And so here's some code. You can tell it's code because it has a jaggedy line rather than like a squiggly one, and so it's more digital in nature, less human interpretable, right? That's what code is. And so then the buffer here gets closed, and this marker array had the ability to say, if I ever get freed because the buffer is closing, call this callback right here. And so it does that, and that means that it called this, and then it passed in some user data, and that user data took it back to this data structure and said, alright, knowing what buffer is getting closed, right? We know what buffer got closed, we know this callback gets called, so this buffer, this with the user data from this guy, comes in here, and now we can say, okay, the user data got me back to this array, the buffer ID tells me that this thing is closing, and so what it would do is it would come in here and go, okay, we don't want to rearrange the array, we just want to zero out all of this nonsense, because I still want this to be index 4, for instance. Now I'm not sure if that's the way that actually needs to work, but let's suppose that is the way it needs to work, because there's a very good chance that that kind of data structure will exist even if it's not this. It could be that in the future someday someone wants to make an array, and then portions of that array can become invalidated, but they don't want the whole array to rearrange when that happens. They want the original structure to remain intact, even though portions of the array have been invalidated. So that, for instance, if they stored an index into somewhere, they can use that index to look at that spot in the array, say, if the thing is still valid, do the jump. If it's not valid, I don't care. If the array automatically adjusted and this became the new 0, they would not be able to discern the difference between this thing is invalid and this thing still exists and has just been, like, they wouldn't be able to tell this is the same thing I marked in the beginning, or versus, again, they wouldn't be able to tell the difference between I marked this spot and it hasn't changed, and I marked this spot, it's become invalid, and my index is now invalid too. They would look like the same when the code executed to go and do the read. So, how do we support this type of thing easily using the same data structure that can easily support that stack thing? Because I think if I can support those two, I will be satisfied that it's a good enough architecture to go ahead with without doubt. But I still have some doubts as to how well I can do this. So, the biggest thing here is I want to be able to do indexing. And the very easiest way to do this is to keep a callback and have that callback just get the user data that tells it how to do this. So maybe I should actually say I will keep hooks as a part of the system because it lets you do something like this. Maybe. Is there another option? Is there an option that is very natural and easy to reason about and repurposable that isn't over-specialized to this problem that avoids the hooks? Because avoiding hooks means avoiding forcing the users to write data management code, which is the whole point. Well, basically another thing that's going to be happening here is not only will this whole thing exist. Well, the one way I could do this is just say here's an array, there is no linked list, and then put this has like each of these spots here knows what buffer it goes to, and so then it can cross over this buffer, the buffer ID, which goes to this, with the buffer up here. Let me do this properly. With the buffer up here, that is the jump list, right? And so by crossing over the jump list and the buffer right here, we get back to this thing. We can also just store a variable right here so that we can look that up directly, right? So you cross those over, look up that variable that is the, given this crossover, what is the marker list, and now we have a way to index from here through to here, and then finally find the position we want. And I'm okay with that many levels of indirection to get there, because it is a bit of a, like, there are several different overlapping concerns that we want to use as the keys to finding that data. It's just going to be a long lookup path. But the problem with that is it means that there definitely has to be a callback. So the idea I had been entertaining was that instead of linking it like that, I would, let me back up to before I even delete that buffer up there. Okay, so now we're back in the state where I initially created it. Here's how we look things up. Instead of storing this array, the idea was, what if I store a linked list? And so this is one node, this is one node, this is one node, and they link to each other using that same data structure we were looking at before. Right here we'll put the sentinel. Right, so that sentinel is the same node on both sides. And so we still have that buffer up here that is the jump list. Right? So here's the jump list, and all of these things exist inside both the scope of the jump list as well as inside the scope of this buffer, the buffers that they jump to. They're intersected, these nodes are, but this thing here, the sentinel, belongs just to the buffer list. So it has a variable saying, here's my jump list, and that points it straight into this sentinel. And then that sentinel, you can iterate it and find all of your jumps. This would automatically work in the sense that now if I use, okay, go to the third value, I could look up, okay, here's this node, 0, 1, 2, yeah, 0, 1, 2, there's the third value. So using this node would have the this node would also have either a handle to the marker array or just would be the marker array if I allow for that many layers of composition of managed object types. I guess I don't see why I couldn't have a managed object type that is simultaneously a node and a marker array, given that I'm already going to use marker arrays as interchangeable with memory objects and nodes as interchangeable with memory objects. Why couldn't a node also be a marker array? I don't know. So this node just has its markers in it, and we say, how many markers do you have? Oh, I have 4. We're looking for the third one, so you contain it. Then we can say, all right, I'm looking for number 3. We're using this node, come to here, and oh, your jump is like right here in the buffer, right? And there we go. That's how we would do the indexing. So the first problem that arises is this is not an array index type API anymore. If I say give me the 10th element, I now have to iterate each of these nodes and ask, how many are you? 4? Okay, so I have 6 left to look for. How many are you? 1, 2, 3, 4, 5, 6. Perfect, it's this one. And the deeper in I want to index, the more iterations I have to do through this linked list, which is not ideal. Now, I could store an iterator by saying we have a sentinel and we also have another node that's our iterator, and it gets linked in somewhere and it moves around all the time. This is what I considered before. Now, you couldn't index straight to 0 very easily, or 0 would still be easy, but you couldn't go straight to 10, but you could iterate one at a time and not lose your position. But that's kind of a mess and leads to all kinds of problems where if you have two iterators in the same list, how do you make sure you don't accidentally treat a node that's actually an iterator as if it were a node with markers in it and get confused by the fact that it's the wrong type of thing? Furthermore, even if I did do this, when this buffer gets erased, yes, this gets auto-invalidated without a hook, but now this looks like index 0, 1, 2, right? So, to really make this work, not only would I be storing the size of each of these things, but I would also be storing their starting index so that I'm really storing the range that each of them covers. So what would be better? What would be better? I'm not sure what would be better. Alright, here we are again, back to the very beginning. What if I do store this as an array, everything in this range links me to this marker array. So if I look for number 3, I go, okay, 3, where's your marker array? It has the pointer to that marker array there. And I say, okay, I'm looking for the third spot in here. Alright, here it is, and then there's my jump. Right? Then when this gets erased, what would happen is, what if I just didn't update this at all? Then when I say go to number 3, it would have a handle to something that doesn't exist and just fail right there. What if that was the idea? What if handles to managed objects don't recycle, so that you get your 64 bits of space, like 64 bits minus 0 because, like, minus 1 because we won't use all zeros as an invalid handle. 0 will always be an invalid handle. And then after a handle comes into existence, it exists for a period of time and then dies, and it is never allowed to be reused. If 4coder gets to the point where it's been on for so long that all 64 bits have been used, that's just like 4coder has to shut down and restart or something. I don't love that. Yeah, I don't love that kind of plan. The reason I don't love it is for debugging purposes. I mean, assuming that we wouldn't actually ever hit it in practice, the idea that it would be there in theory is still uncomfortable. But in practice, I still don't like the idea, because if I'm looking at a handle and I'm not sure if it's valid or not because it could look valid but not be valid, is not great when you're debugging your code and you're going, okay, we got a valid handle, and we look it up, and then we didn't get anything. Oh, I guess it's invalid. Now we want to track down when this became invalidated, which means we're going to need a hook for that anyway. What we do have that solves this is the variable lookup system. The variable lookup system doesn't suffer from that problem, because with variable lookups, if I set a variable into buffer 5 and then later I go and read it and it's gone, that means that buffer 5 closed, right? I try to read this variable and it's not there. Either means buffer 5 is still closed, or buffer 5 closed and a new buffer has been created and recycled that ID, but that value hasn't been set in that buffer yet. And that value hasn't been set because I haven't set it, and I, being the module that created that variable, am the only one who's supposed to be using it, so I can reasonably infer that it's not the same buffer, and therefore I shouldn't expect to find any state in there that relates to things I've set up already, right? If the things I've set up aren't there, then I haven't touched that buffer yet. That's the idea. Which means what we could do Yeah. What we could do is say we don't store the buffer ID exact directly. We store the exact array, and what we're going to have is we have the buffer up here. And so the combination of this has a buffer ID, and then this has a buffer ID in it. And so we want to go to index 3. We look up index 3 and we say, okay, these two buffer IDs, get the managed scope that is intersected between the two, and look up a variable called the, whatever, the sticky jump handle or whatever. And if that exists, that means we can infer, one, that this module set it, and two, this module set it when this buffer was created. And since since these things only get set during the creation of this buffer, this must be the same buffer that it was when we created it. There it is. That's what we do. So we don't actually need the linked list for this problem. The linked list will be handy for problems that want to do stuff like stacks and queues that do change order, but for things that want to keep their order, we won't use that. What we'll use is this lookup system right here. We store the ID of the buffer we care about, and at creation time, we have some other scope that we cross that over with, so that if this buffer closes and a new buffer with the same ID ever opens, I guess even if that doesn't happen, if there's only one of these per buffer, right now part of what's happening is there are multiple sticky jump lists per buff, like, in existence. But if there was only one, we wouldn't even need to do this crossover and the system would work. It's just whatever the unique key is. Yeah, there it is. Okay, we've got it. Yeah, so what this needs to store is it needs to store the ID that matches this guy's ID, and it needs to store its relative offset in its bunch. So this is a 3, this is a 0, so that if we index to number 5, we come here, we get the ID for this buffer, which is some buffer down here. We look up its thing, and we go to the 0th spot in its marker array. Young Lena asks, do you have a list of features that you're working on somewhere? You know, kind of, but not really. Let me look up real quick how the roadmap.html looks right now. So this is a very poor list of things I'm working on. I might update this soon, but this is the best public list I've got. It's missing tons of stuff because I come up with small things along the way. This fix up the undo redo system is happening soon, and the rest of this is like this is happening not too long from now. This is happening someday. Who knows when that'll happen? None of this will happen sooner rather than later. This list is really poor. I guess there's not really a list. Jim asks, how far off do you think 029 is? I don't know. I'm kind of pretty far on the deep end here. We're going to get this managed scope stuff figured out today, I think. We're going to implement the thing I just came up with for the jump lists, right? The jump list will be restructured again to use that system, and that will mean I won't have to implement the linked list version of a managed object right away. I might still put it into this build, but I won't do that now necessarily. We'll think about it. Once this is working, I'm going to get back to the lister stuff for a little while, and the reason for that is the existing listers need a bit of tweaking to have all the features that the other one had. Once all the case insensitive file matching wildcards and that stuff is back, then I'm going to build a few new lists, just a few, and then I have some other stuff. We're going to do the undo redo system. We're going to do by the way, these have all been checked. Yeah, I don't know. I feel like this is going to be like the last big build of the year. It might go on all the way until like October or November at this point. We still want to do marker types, so like visible marker types, line highlights, cursors, skinny cursors, hollow cursors, range highlights, maybe even text fades, or like text colors. Although I'm not sure about that one. The fading, implementing the text fade through the marker system is potentially possible. It's just, I feel like that's slightly more specialized because you probably want to have the core manage the fade for you, so you can just issue it and then forget about it. In theory, you might also want the ability to say, I put a marker down that's like from here to here and color it purple because buffer summary, whenever I parse that out, I want to color it purple, but then you're in this really nasty spot where what if I do this? You're not supposed to get notifications on that kind of thing, so what would happen? Hollow cursors, like the marker, like the mark, like that thing. The wireframe rectangles, the wireframe cursor. Once all that stuff is in there, I feel like we'll be past August, somewhere in September or October, and I will reevaluate then whether it's time to ship or not. I think by then I'll be ready to get this out. I really want to write a lot of example code to go with the new stuff. Okay. So this is wrong, mostly, somewhat. So this gets the dynamic scope of that, gets a list sentinel, no, we don't want that. For each range, get the target buffer of the range, get the number of jumps in the range. What's happening here? So we're buffer add markers, jump count, marker temp, again temp memory markers, fill up. So here we're setting the initial set of markers. Here we're creating a memory object, a plain memory object. And that is getting the line, colon, index, and sub-error flags. That I don't want anymore. That is going on a per buffer basis, and I actually want to store that information in the jump list, because even when it becomes redundant, we'll just let it sit there taking up space, I think. Because at least then the indexes will be able to remain consistent. So that's all wrong. This here allocates a node and then sets that node to have the handles back to the memory and to the markers and to the number of jumps in the node. Okay, none of that is relevant either. That's gone. Okay, so this actually needs to work is we're going to create a memory object up here. A managed object, my bad. I'm going to create a managed object that is the just the like jump array, or yeah, and that'll be a managed memory alloc. and I'm going to put that right on the scope array 0, manage memory, alloc, line details. Yeah, so let's take a look at what that is. Line details. Yeah, so what we're going to do is change this to jump stored, and that will be very similar to this. It'll have this, and then it's going to have marker index into marker array. Wait, I remember why I didn't do this before. I didn't do this because I was worried that it's... Milton is gone. Milton, come back. Okay, before we continue, there's one other thing to consider. All of that works, and that's the easy part. Unfortunately, the hard part is what if this is buffer 13, and this is buffer 13, and this down here is buffer 13. If this was buffer 13 here, then this could just merge into one block. But what if the order looks like this, and so it goes 13, I don't know, 21, and then 13 again, right? Then how do we do this? Because if this has a variable block that says when you cross this ID here, which matches this ID, with this ID, you get this nice crossover scope that takes you into here, and you say, hey you, what at variable index blah, whatever my variable name is, where's your marker handle? Oh, here's my marker handle. And then he says, oh, go to number 1, and that takes you right here in the buffer. Great. But what if at the same time this down here also matched this? Now what happens is we have two different sections that both want to have a marker array in here. So my options are I can have two marker arrays, but now when I'm in this one, how do I find the right one is the problem. Right, if these are just floating here and I have one variable that can look at this, I can't also have one variable that can look at this because I can only have a finite, I have to have a fixed number of variables that I planned out. And so what's really happening here is I'd really like to be able to say this variable goes to some kind of an array thing, and that array looks like this, and then goes boom, boom. And so if I'm in this one, I know that I use the second array, or the second value in this array, to go to here. But that's so many layers of indirection that I'm unhappy with it. So another option is that I just do more work in the implementation of the jump list and say that we have one marker array that goes for 4 and then for 5 more, right? So there's the first 4, and there's 1, 2, 3, 4, 5 more. And so now this and this can both come to this one spot, come here. He says I'm 0, like these go, my sub-indexing is 0, 1, 2, 3. Then this guy goes for a little while, and then 4, 5, 6, 7, 8. So that if we're here, we just know to go to this one to get our, we cross these two over. We get this variable block. We use the variable block to find this marker array, and we use this to find the jump into the buffer. Right? Only question is, once that data structure is built, we're golden. How do we build it now? That's what we need to build. How do we build that? Right now I'm receiving a series of ranges. But I kind of want to sort those by buffer ID. So if I made an array of pairs where the left value was the index into the range array and the right value was the sort key, which is the buffer index, sort them by the key, then what I would be able to do is oh geez. Wow. Then I could assign back to each range a total count, and a start within its sub array. Correct. Okay. Alright. You guys ready to get nutty? We're gonna do some craziness. I'm so crazy. Is this really the way I want to do this? I mean, the data structure is simple once we're out the other end. I can decompose it into very manageable chunks. It's not that hard to implement. It's so much more work than I would have expected to need to do. And the reason it's so much more work, the problem I'm running into here is that it's possible that the key of a pair of buffers isn't unique enough to identify the thing I'm looking for. If the key could be like, I'm just saying, oh, you know, each of these understands themselves to be the first instance of this, and this understands itself to be the second instance of this. Then when I put in a 1, I'm saying that I actually want, right, and these would be separate from these numbers here. Maybe I should draw that like so. Right, separate numbers here. These numbers that I'm putting a red box around represent the subkey that I want to use. Then what could happen is I say, here's the two buffers and the subkey. The two buffers helps me look up into the system the thing which has its lifetime tied to those. Whether you have a subkey of 0, 1, or 10 million, you have the same lifetime, right? The scope is the same. It's just a matter of the subkey being used to split things out easily. This would make this very easy to implement, because then what I would end up with is oops. Two, three, four, 5, and so then we would have two of these. They're kind of split by, you know, one of these, with this being the 0 subkey and this being the 1 subkey. And so then this would index to here, which would index to here, and then to here. Whereas this would index to here, and then to here, right? This would make it very easy to implement this in the natural way. Later, young Lena, thanks for hanging out. This would make it very easy to implement this in the mostly natural way. I would still need to get a unique integer for each of these, which would probably entail sorting by buffer ID, and then taking ranges of repeated buffers and assigning each one an integer and passing that all back out. So I would still end up having to do some of the craziness anyway just to get these unique keys. But this might be a feature that is useful to support anyway, because it basically means that all of your variable blocks can have a sub-index that is used for, well, it's used for saying, like, here I want to go to this variable and I want to treat this variable as kind of an array. The other option is that I say that every one of these variables has the potential to be an array. So instead of treating the subindex as I go to a variable and which variable block I go to is determined by the subindex, it could be that there's one variable, there's one space, there's one scope, and both of these exist inside of it. And this is a picture I already drew once, but maybe conceived in a slightly different way it would be better. And then suppose I have a variable here that acts as an array because it's got like a 0 and a 1. So it's like I am this, and this can be, you know, a sparse array that can have any amount of indexing complexity that it wants. But once we found the variable, we get this sparse thing, and then this can go to here, and this can go to here, and, you know, this doesn't actually exist. And so the advantage to this method is it lets me keep the basic structure that we have now, that there's one single variable block that corresponds to the managed scope, and if there are like some things with like 10 spots and others with just one, this doesn't have to have like itself extended out to here once for each like slice, right? If there's like this, and this variable never uses an index and this variable is using tons of indexes, I don't want to have this sitting around and doing nothing, which would happen in the other format but not in this one, or could potentially be happening in the other format depending on how that one is implemented. It could more easily be happening, especially given the way variables are currently implemented. So would I like to do this? The problem with this is the only way this really happens is via an indirection, so that the variable has a particular value stored into it and then it indirects to another data structure that actually has the sparse indexing. And the reason I'm not too thrilled about that is a lot of times all I want a variable for is just one 64-bit value, which means that what might end up happening is I want, like, well, yeah, the problem is no matter what I do, I end up having to count this as 0 and this is 1, right? I end up having to figure out those values there, and even with that information, that's a 0, that's a 1, I still have to decide, okay, if that's a 0 and that's a 1, do I pre-allocate to here, or do I get to say any index I want and it sparsely fills out, making yet more complexity in the core for supporting these things, all just to avoid allocating these two things together once we've already had to do the work of the sort. You know what? I think we'll keep it simple and force the custom layer to do a little bit of heavy lifting whenever it is encountering this limitation, because worst case scenario I decide that this limitation is too onerous on the custom layer and then I implement these features in the future without really interrupting what I've already got. But for now I want to assume that this is good enough and let so that I don't have to implement lots and lots of new core stuff all the time that may or may not actually need to be there. If I implement new core stuff that doesn't really need to be there, it kind of will get stuck that way, where more heavily than if I don't implement stuff that does need to be there, I can add it. So what I will do is I will add in the get set variables, in the get or set variable calls, I'll go ahead and add a 0 flag or a 0 field so that everyone for now is putting zeros in right there, so that their code will still compile if I add that feature in the future and say, hey, now you can put 1s and 2s and 10s here to get different, like an indexing scheme. And all your code that you wrote before there was an indexing scheme will just have zeros there if you've done it correctly, and so it will keep working as ever it did, as it always did. You know, that kind of for future expansion parameter type thing. And so we're going with 4 and then 5. 1, 2, 3, 4, 5. The other thing I don't like about that is even if I did have this, right? Here's what where my brain goes. Even if I had this, right, and so we can have these arbitrary arrays, maybe sparsely filled, that are attached to each variable, and then those things are the 64-bit values that point out to each of these things. I still have the problem that what if I end up in a situation someday where 2 buffers and 1 integer isn't enough to specify uniquely the thing I want. That's always going to be possible, that 3 fields aren't unique and a 4th field becomes necessary. And so constantly like extending the number of unique keys to handle that whenever it comes up isn't really a maintainable way to handle this anyway. Like one way or the other, someone has to handle the fact that you need this many fields to make a unique key in your system. If I'm handling it, then that means I'm making something that can handle n unique fields for a key, whereas if you're handling it, I can make a thing that has this limited scope of what it provides, and you can customize your keying on top of that as necessary. Now that's not to say that this wouldn't be a good idea, because maybe this is the amount of keying that if I provide makes it as easy as necessary for everyone else to do what they need. But all of this can be implemented from the custom layer for now. It's easy to make it robust for expansions in the future. I think that we'll go with this kind of system with a 0, 1, 2, 3, 4, 5, 6, 7, 8 type thing. Okay. So to do that, we make a jump array, and the size of that jump array needs to be the size of a sticky jump stored times the number of jumps. And I better close Milton again, because leaving it open while I'm programming is always bad. Between Milton, 4coder, and OBS, things just frame rate plummet. Okay. Now we're ready to get to some code. So I allocate my managed object that has enough memory for all of those jumps, and I stick it inside the jump list buffer ID thing, and then what we want to do is we want to compute that jump array, which we can do by saying sticky jump stored. Well, why don't we do this? We're going to put this down here. Sticky jump stored will be the stored values, which look like this. We put them onto the partition. We put them onto the partition. We want that many of them. And then so we're going to loop across the range here. And for each spot in there, we're going to take stored j dot list line equals jumps dot jumps j dot list line, and we want the same thing for list colon index, and we want the same thing for is sub error. Okay, and we want the same thing for jumper buff ID, or jump buffer ID. The only difference is instead of storing a jump position, we want to store the index into the jump array, which is where things get weird. Because in order to do that correctly, what we need is, we have buffer ranges, we want Alright, and then we're not going to pull this out into a function because it's very much it's very specific to this. It doesn't really lend itself to easy naming or reuse in other parts of the code. So we're going to visit all of the pairs, and for each one, we're going to say set the index and then set the key. The key will be the buffer ID that we get when we look at jumps dot buffer ranges jumps dot jumps index into buffer ranges dot ranges I dot first dot buffer ID. Then we're going to sort pairs, which will just go range index buffer ID pairs buffer ranges dot count. And so now we need to take a step back and go visit let's see, helper.h and CPP. I'll stick these here for now because, you know, who even knows? Who even knows? We're going to go with int 64t. Well, let's go with 32t. I'll call this sort pair I32. Index and key. So there's our sort pairs, index and keys, and then we just need to be able to sort them. Sort pair I32 pairs I32 count. That should be int32 count. Sort pairs quick pairs 0 count. sort pairs quick, first one past last. If first plus 1 is still less than 1 past last, then we need to get a pivot, which we'll get that in a second. Sort pairs quick, then does pairs, oops, get out of here. Pairs first pivot, and then pivot plus 1, 1 past last. Now pivot is going to equal 1 past last minus 1. Then we'll say int 32j equals first. For int 32 I equals first, I is less than pivot, I plus equals 1. Int 32 key, pivot key, equals pairs pivot dot key. If now what we want to do is the whole swapping thing. If the we'll get the key, which is the pairs I dot key. If the key is strictly less than the pivot key, we're going to swap. I think that means I'll have to do this. T equals, why don't we just do this? I equals whatever is stored in J, and J equals whatever is stored back in the key. So that does a swap. Else, if the key equals the pivot key, this is something I've been doing in my quick sorts recently. Interleave equals false. If interleave, then we do the swap. Else, either way, interleave equals non-interleave. That way, if we have an array that's like a lot of duplicates, then we won't end up in a situation where we pick something and it's like 1/3 of the elements are smaller than this, 1/3 of them are bigger than it, and the other third is equal to it, and so the final third is equal to it, and so you end up with like bad splits over and over again. Instead, what will happen is if you pick something that has a lot of stuff that are equal to it, then you actually got a very good pick because it'll interleave stuff on both sides of the partition. It's not so good if you care about it's not so good if you care about stability as in keeping the same suborder within equal elements, which I kind of do right now, I just realized. I kind of care about stability. Well, do I though? I actually don't need to care about stability, do I? No, it would be extra work, and actually the algorithm would not fail. It would just be unexpected and odd that earlier things have larger indexes than later things, but it wouldn't actually cause the algorithm to fail. So I'm fine. Okay. And whenever you do that, you also increment j by 1. Then, at the very end, you swap the pivot nj. So to swap the pivot nj, what you do is you say pairs pivot dot key equals pairs j dot key, pairs j dot key equals the pivot key, and then finally we're going to set pivot equal to j. So what that has accomplished is it's bisected the array into the things that are smaller than and larger than the pivot, and interleave the things that are equal on both sides of the pivot, and then put that pivot right into the correct spot in the sorted array, and returned and stored into the value pivot the result of that whole iteration, which we then use for this. Technically, I guess I don't even need to do that. I could just use j here and here to determine where the next two quicksorts need to happen. This recursion will end as soon as the range between these two drops below 2. As long as there's not at least 2 elements to sort, it will continue. Now, for an optimization, what I could do is say, first of all, let's just do 1 past last minus first. Right now what I'm doing is I'm saying if the difference is greater than or equal to 2, we do this. Technically, if the difference is equal to 2 or maybe 3 or even 4, there are faster things I should be doing. So if I ever want to optimize it, that will make it easier to write the optimizations. But I'm not going to for now. I will leave it in this state and let it recurse all the way down to the very leaves of the recursion. And, you know, that is that. Now, if we get back to the sticky jumps, we fill up these, we sort by pairs, and now what we have is an array that maps, that groups ranges together that all have the same buffer. So then what we can do is say, let's get I guess we're going to get ranges of those ranges. Yeah, so we're going to get range array. So those are the buffer ranges. This is the range, and this is the grouped buffer ranges. And this we will get right over here. Range array, get ranges of duplicate key, sort pair I32, sorted pairs, partition arena, result, return result, etc., etc. So this is get ranges of duplicate keys, scratch, okay. And this is basically the same thing as this again. So I might want to dedupe this. And so the only difference here is instead of looking at jumps.jumps all the time, I'm looking at count, and then I'm looking at sorted pairs. Doesn't even really need to be sorted pairs now that I think about it. You might want to be able to do this on an unsorted array and find out its ranges like I did earlier. Hey, Croifa, how is life? How's it going, Dave? Okay, so if pairs I.key does not equal pairs start I.key, yeah, I should probably deduplicate these two things, which is basically just a matter of saying that there's a stride element, and that stride element probably wants to be measured in bytes, so what we'll end up having to do is have a like a base putter right here that starts on the keys, and then in order to index the keys, what we have to do is we go putter plus I times stride, dereferenced as an I32, and then same thing again with a start I. Then that can get erased. Mark buffer ranges just becomes get ranges of duplicate keys, scratch, jumps dot jumps buffer ID, size of one of these, and how many of them are there? Jumps.count. This one down here becomes key, size of one of these things, Wait, are you working on like a kernel? What do you mean kernel module development? Are you talking about a debugger, like a kernel debugger? I didn't realize you were adding kernel debugging. That's crazy. But maybe I just don't know Linux terminology well enough to know what Linux kernel module development in the debugger means. Okay, so how are we doing so far? I get the ranges of the buffers that or I get the ranges of jumps where they all share the same buffer. Then I make a sortable list that is keyed by buffer and carries the range index with it. Then I sort that array on those keys. Sort pairs by key. And then I get the duplicates in that on the keys. So now if a buffer appears ever, it appears in one range here. It appears in one or more ranges here, and in each of those ranges it appears n times, right? In here, for each range, where n varies per range. So now, what I should be able to do is I can build up an array that is the total. I can build up the total count and the assignment of the starting index within the whole buffer for each one of these. So I'm going to need two integer arrays for this. Buffer total jump count. Total jump count will work. Push an array onto Scratch of int32's grouped buffer ranges count, and then a separate one that is per range, which is the jump or buffer range first index array, which we can put onto Scratch, which is an int32, and is by buffer ranges count. Okay. Then, for the grouped buffer ranges, we get a total count by going we're going to get the range, which is the grouped buffer ranges I, for each of those, I can then say, alright, here's a range in the buffer ID. So when I sort them, what happens to them is they end up like this. I have all the buffer IDs next to each other and the range index is like this. So I want to look at range index equals range index buffer ID pairs j dot index. There's my range index, and that lets me get one of these ranges, buffer ranges dot ranges range index, right? So for each of those, why don't I just store... Okay, well I guess I do need to store this much information, but I'm storing that there anyway. Why don't I actually just do this? Okay. So I get a range, and then I'm going to add to the total count. I see. So GDB comes with basically the kernel module debugger, and you're just, you know, dealing with all the Linux nonsense that happens when you try to do something with the Linux kernel, like rebuilding your kernel or something with debug info, or getting the debug info for your kernel or something like this. I could see that being a big pain. Sounds very Linuxy. Okay, so that gives me the total count of all of the jumps for this buffer. With that information, I am now poised to allocate onto this scope here. Let's see, we want to get the target buffer ID. Alright, so I grab the target buffer ID by going to range first. I have to get a range, which I can get by going here. And I gotta get a range index, which I can get by going here. Okay, this is getting too nutty. So instead of all that, what I'm gonna do is say, please, while you're doing everything else, find out my target buffer ID, which you have a unique opportunity to do right here. If target buffer ID is still equal to 0, set it to the jump range first. So in this grouped range, we get a range of indices that give us the ability to look up like sub-range indexes. Each of those sub-ranges is non-contiguous with one another. The first one of those, if I grab its first index into the jump array, then I can get the jump and pull out the buffer ID. And so there's the target buffer ID. Now I can say get the dynamic scope that we care about. Probably going to rename that to a managed scope. And then buffer add markers. So the number of markers we want to add should be equal to total count. We put them into that scope there. And then we say, alright, we want to fill all of these markers and then set that marker handle that we just allocated. We're actually going to redo it like this because I feel like that's better. Now the problem is, how do we want to go about... Oh, why don't we reorder this a little bit more and say we grab the scope down here. As we are getting the total count, we could also just start grabbing these one at a time. If we give up knowing the total count right there, we can find the total count at the end by doing a little number like this. Total count equals wherever we end up minus the number of markers we grabbed. Along the way, we'll just be putting down new markers. One at a time. Each new marker will set the position and the lean right. And then, let's see. Then what we can do is set this right here to be k equals range dot first. K is less than range 1 past last. K plus equals 1. And then grab our jump out of k like that. So we grab a new marker off the arena. We fill its position by looking at by iterating the k values inside this range and putting jump position in each of those. That fills up our new markers. Cool. Now the only other thing to deal with, and that means we've created all of the marker handles that we need. We still need to store those marker handles somewhere useful later. But that part won't be too hard. I think we are done with this part and this part now. The only remaining little hiccup before this really comes together is once we have those markers, we want to fill in the stored index into marker array, right? And so I think for that what we want to do is we want to be able to say that we have I guess total count will be an incremental thing in this case, because we're going to put that right there, and every time we make a new marker we're going to eventually take total count and add 1, but before we add 1 we're also going to look up the stored thing that we need. So the stored thing I think comes from k, and then we can set the index into marker array equal to the total count. Alright, so now what about the rest of these things? Why don't those just get set up there during that iteration now, right? Because we're already visiting all of the jumps through that iteration. What's the point in doing a separate iteration to visit all the jumps again? Besides the fact that this iteration is in order, we already have to touch that memory once in an out-of-order way, and then we're going to touch it all again in an in-order way just because it lets us do it in order, but we didn't avoid the out-of-order case anyway, so we're already bottlenecked on that small amount of jumping around that happens every time the ranges are discontinuous, like over a long jump. So once we've loaded in that memory anyway, we might as well just fill the whole thing, right? Let's try that again. There we go. And then that can hang out right there. So what we're doing is we parse out our jumps. We get the ranges of the duplicates buffers. We get an array of buffer IDs as keys and range indexes as values. Sort that by the key, and then we find the duplicates in that thing, which means that now each buffer has exactly one grouped buffer range, which is a range in this array, which gives us indexes back into this array, which gives us ranges into this array. Nutty, right? This is why I was avoiding going down this, because it's like what is this? This indexes into this, indexes into this, indexes into this. It's four levels of, let's see, this index. So there's one. Index, 2, 3. 3 levels of indirection. To make this work. Fill the marker array, and then we, along the way, we fill the stored array with all the information it needs from the jumps. So we're building up new markers as well as filling in the stored array at this point. They each get an index which corresponds to where the marker was placed, and then what? Then we get the dynamic scope that intersects between the buffer, the target buffer, and the jump list buffer, and we use that to allocate the new marker array, and we set the marker array from the data we have right here. Good. We still need to set a variable that references the marker array inside that scope, and then we eventually need to put this, the stored data, into this. Alright, I need to take a 5 to 10 minute break, and I will come back and do the things I just said I would do right afterwards. See you in a minute.